our second speaker, Nimbus Goehausen, is Senior Software Engineer at Bloomberg. Please welcome him.
Hi everyone, I'm Nimbus Goehausen. I work on the Spark platform at Bloomberg, and Bloomberg, if you weren't already aware of it, has its main product as the Bloomberg Terminal, which is the premier data platform for financial professionals. There's a lot of data, there's a lot of activity, and there's a big emphasis on real-time accurate results for our clients. But I'm going to talk about something a little different. That is offline batch processing development. So, because there's a lot of data, there's a lot of activity, you accumulate some interesting history of data, and there are things you want to do, such as machine learning models, back testing, to kind of generate indices that you can deploy to like search indexes and so on. So this is the basic thing that I'm talking about. It's the data pipeline. And let's be a little specific about what I'm talking about. So you're taking in some kind of input data. You're running some kind of process over it in order to produce some kind of output. So this could be maybe a bunch of different tables that you join together and then featurize, turn into vectors, and then run some kind of machine learning algorithm over them in order to produce a model. And then maybe you might further validate and backtest that model against data it wasn't trained on. And specifically, I'm talking about doing this in Spark, and I'm also talking about doing this as part of like a library you're developing. So there's a number of kind of prototype things that you can do in a notebook. You can get pretty far with just a notebook, but at a certain point, once your process gets a little complicated, you probably want to put that in a repo, have a whole project, have that in a library. And if you're in that position, this is a development cycle that you'll have to worry about. So you can certainly do a lot locally with a small sample set. You can make unit tests, you can run your thing, just make sure like, okay, well, this compiles, seems to run on some sample data, but you really don't know if this stuff is going to work until you actually run it on the cluster with the full data set. And once you want to go and see that that works, it might in fact fail, or even if it worked fine with a small sample set. So when that happens, you have to worry about this cycle. So you'll make some code change in your library. You'll have to repackage your library, deploy a jar to the cluster, and then resubmit it to the cluster, or perhaps start a interactive notebook session, and then you'll have to wait for it to run. And it'll do something, and you'll see what happens. Maybe it does what you want, maybe it doesn't do what you want, but you'll observe those results, and if it all worked fine, then you're done. You got what you want. But if it didn't, then you have to repeat the process. You have to make some kind of code change, redeploy it, re-execute it. And so certainly some of these steps are, they're a little tedious. It'd be nice if you could get rid of the jar deployment and the resubmission and stuff. But typically, what takes the longest in this is the actual execution time of the job. And it depends on what you're doing. But for a lot of non-trivial data sets that you're doing a non-trivial process on, it can take a while, like a few minutes to a few hours. And so what I'm going to talk about is something we can do to make that shorter, just to do as much as we can to make the development cycle faster. Because really, what we would really like to do is spend all of our time at the top two regions, that is, making code changes and observing results. And as much as we can spend more of our time on that instead of waiting around, the more effective we'll be. So here's our data pipeline again. And magically gone and run it on some sample set, some files, it seems to do what we think it should do. And then we go and send it to the cluster. And then something like this happens. And often there are many useful error messages that come out of Spark. Like fairly often, it's a pretty trivial thing. You see a line in Len2, and it's a quick fix. But that's not all the time. Sometimes you run into things in which it's really unclear as to what the problem is. There could be a lot of things to blame. It could be your code, it could be the environment, it could be the data, or it could be a mix of those things. And when you run into something like that, the only choice you have is really to run it again, maybe checking on some earlier stages, seeing, changing what you're observing, but you're going to have to do some kind of experimentation. So, because this takes a while, a lot of people will do something like this, where they want to save intermediate results. They have this pipeline. It seems like the first half of it is working just fine, and there's some kind of mysterious problem in the second half. So instead of just rerunning the whole thing every time, and rerunning the first stage over and over again, even though it seems to work fine, people will split these up. So now we have stage 1 as its own, has its own main entry point, and stage 2 has its own entry point. And when we run stage 1, it saves to a certain spot, and then when we run stage 2, it reads from that spot and it does its thing. And this is better because now we can debug our mysterious problem that's happening in stage 2, and we can do it quickly. But by doing this, by kind of trying to improve the performance, we've kind of complicated this more than we would like to. So there are problems we introduced here. One of the problems is that stage 2, we can't run that without having run stage 1 first. So just by default, if we were running this in some environment, we have to make sure that we run stage 1 first and then stage 2. And also, say we realize that the problem happening in stage 2 is actually a result of incorrect logic in stage 1. Stage 1 is running fine, but it's producing the wrong result. So then we have to go and change stage 1. And when we do something like that, then we have to make sure that we either overwrite the output that was already saved, or we have to save it to a new place and make sure stage 2 knows to read from it. And that's a pain. And if the problems get worse, as we might have more stages in this, and also they get worse if we have multiple people working on similar things and sharing intermediate results. It's a little more, it's a little more than we'd like to manage. And so here's something. Wouldn't it be so nice if we could just write it like this and it did what we wanted to do? So we have a single entry point once again, but we just say that stage 1 will be checkpoint. That is, the first time it runs, we want it to save, and the second time, as long as it's what we want, it'll be loaded and fed into stage 2 without stage 1 having to run again. So specifically, we want it to work like this. First time we run it, we save the output from stage 1, and we also pass along that output to stage 2 and run as usual. The second time, we don't want to run stage 2, or stage 1. We just want to load the output that we already saved and run stage 2 over. And if we happen to change stage 1, we want to make sure that we're saving to a new place, we're recomputing things that we know, because we have a change in logic, we have to do the computation fresh. And we want to disregard the previously saved output and feed the new output into stage 2 and save it. So now, how do we do this? I kind of, this is just waving my hand, so it would be nice if it worked this way. But how can we accomplish this? So let's remember a couple of key things. So the checkpoints should stay the same when we want to reload the same data. So we need a path here. So first of all, I just kind of, this checkpoint, this kind of code that we would like to exist, I'm not passing a path. I'm sort of saying, we'll figure it out. And so we need to figure out a way to generate this path automatically. So it should stay the same when we want to reload the same data, and it should change when we want to generate a new, that is, there's a change in logic, or it's reading it from somewhere else. So little, refresher on Spark. So RDBs stand for resilient distributed data set, and the resilient part refers to the ability of Spark to regenerate partitions based on the need. So it's robust in that way. It's resilient and robust in that way. So if you have an RDB here, as a result, it has some number of dependencies between 0 and any number of RDBs that an RDB depends on. There's logic applied to those previous dependencies, and in order to produce the result. So, and if we lose our result, we can just do this again in order to get it back again. So as an example, say we have like a collection of numbers, 1, 2, 3, 4, 5. We map some function over it, like we double, x goes to x times 2, and then our result would be 2, 4, 6, 8, 10. So this is, we have, so that means that the result here, if we happen to like lose track of that result, it's okay, because we can always recompute it again. We've got this logic, we've got these dependencies. The definition of an RDB only depends on the logic and the dependencies. So because of that, we can try to create a signature that captures that. So our result is our logic applied to the dependencies. So let's try to make a string here that we'll call a signature, and we'll say the signature of that result is the hash of the signature of the dependencies plus the hash of the logic that we're applying. And then we'll hash that all together to produce final signature. So as an example, like if we have RDB2 equals RDB1.map some function f over it, we want to get the signature of RDB1, that's our dependency, and then we'll want to hash f, and then we'll want to hash the concatenation of those things, and that's our signature. And now for some things which doesn't have a dependency, like say it doesn't have an RDB dependency, if it's just like the source RDB, that we're loading a text file from some hash or URI, the signature is just the hash of that URI, and then we can throw in a string constant there as well to differentiate like between text files and object files and something like that. So now I just waved my hand to say, oh yeah, just hash a function, but there's not exactly a built-in way to hash a function in Scala, but there is a way to do it. So if you have a function, let's say x goes to x times 2, what Scala does currently, and it is changing in Scala well, but currently it turns into a class for each anonymous function, and you can get a reference to that class with the reference to that function. So each anonymous function will have a class. You can use data bytes. You can hash those bytes, and that will give you a pretty good hash for the logic of that function. And in particular, if we change f, like x goes to x times 3, that class file is going to change in our hash of the bytes. So that's the easy part. The one issue is that certain functions have references to other things. So imagine we have a more complicated function. We have a function that makes references to runtime variables defined on other objects or whatever. We have static method invocations that are defined elsewhere, and we have references to other functions. And what happens if those things change? Does the class file for f change? And the answer is no. That just makes references to those things. So what we have to do is we have to figure out what class files our function depends on. We find out all the dependencies, find all the class files that we depend on, and we make a combined hash. And that, and then we have one. And to do this, it requires using like a assembly, like JSM library for Java. It's a little tricky, but here's doable. And so now let's go back to thinking, okay, if we have this logical signature, what are we going to do? We have a way to generate these paths automatically, but how do we make this happen? Because now we have to worry about actually switching in these things, because that's what our goal is to have a system that switches in RDBs or loads check, use refresh or loads from the checkpoint, depending on whether there's something there or not. So we need some kind of abstraction to do. And there's a couple of options that we could do to make this happen. One thing is to just directly change Spark in order to make it behave like this. Or we can build on top of Spark, introduce an abstraction, and make it happen that way. And I've opted for the abstraction, one of which is I generally can accomplish something by just building on top of something instead of changing the underlying thing. That's usually a better approach. And there's also another reason, which I will show in a couple minutes. So here's an abstraction. I call it the distributed collection. It's pretty much the same as an RDB. It maps like an RDB, it flat maps like an RDB, and so on and so forth. And it can be instantiated without a Spark context. It's just essentially a pipeline method. And if you want to get the corresponding RDB, all you have to do is pass in a Spark context. And also, it automatically computes the logic second. And here's an example with some code here. And as you can see, it's almost the same, except instead of starting with this parallelize, we just start with this function called parallelize, which instead of returning RDB, returns DC. And then we sort of have this, Spark is already lazily defined. Now we have a slightly lazier definition so that we can get the same answer if we just pass in the Spark context. And now we can checkpoint these things. And the first time it runs, it will compute the results and save them somewhere. And the second time it runs, if it sees that there is a corresponding path to that logical signature that exists in the file system, it's going to load from there. So now there's a problem. The problem is, what if we have kind of functions and tendencies that depend on the computation of the result. So here's an example. Let's say we want to we have a bunch of numbers. We want to normalize them such that they all add up to 1. So in order to do that, you need to do the sum, and then you need to divide every element by that sum. So now the problem is that our function here, our last function here, to define our normalized result, depends on this function. X goes to next to the sum, and that sum requires us to actually do the sum. So if we wanted to hash that function, we would need to have that sum around, and that's a problem because if we want to checkpoint this thing, we're going to have to still do the sum each time. We don't want to do that. So this is the other reason why it makes sense to go on top of Spark, is we want a way to define this lazily. And here's another abstraction. It's called a deferred result. And it's defined by a function under RDB. It's like a DC, but it only ever has one thing in it. And similarly, you pass in a Spark context to get that result. It also has a logical signature. And in this, we can express entirely lazy pipelines. So to fix that example now, to make this lazy, we'll call a .sum on this thing. But instead of returning a double immediately, actually going and carrying out the computation, we'll just leave it in this lazy routine, called a DR. And then when we want to define normalize, we'll have to kind of define our function in a slightly more interesting way. We'll have to take the RDB of doubles. We'll basically zip it with the results of our sum here, and then we'll map a function over it that takes in 2 frames, the original elements, and the result that we're zipping with them. And then we can define our function. And this is entirely lazy because it doesn't have to use the sum when we've done this until we actually want to get a result. So this means that we can checkpoint normalize or anything that depends on normalize, and we don't have to reuse the sum every time in order to load a checkpoint from some later stage. So, why did I go to all this effort to use this? And it's about making the overall work. One, we want things to run fast. We want to iterate quickly on these things. We have to but we would also like to avoid making overcomplicated things. So it's nice to be able to write things as if they're one straight shot, but have nice tools that will shorten the work for you. So we want to get the benefits of avoiding this redundant computation, but we also want to avoid the cost of having to manage all these things. Always worry about what goes in, what comes out. Stuff along the way, you just want to write it as if it's a straight shot. And also, because I've gone through this effort to find distractions, there are other things we can do if we're in a position to be switching checkpoints. We can do things such as automatic failure traps and generating common statistics automatically. So there are fun new things. So you might be asking, can I just use this now? And unfortunately, no. I'm still kind of polishing it a bit, making some examples of application. But there is an open source release in a couple of months. It's going to be called Smart Flow. And yeah, if anyone's interested or wants to ask me questions about it, come talk to me. And yeah, any questions about any of this? So people will kind of do this on their, without, this doesn't exist. This doesn't exist. People are kind of doing this anyways as saving in stages. And one of the benefits of Smart is you can run it as like one straight shot without having when you run the new MapReduce, it's staged already. Basically, you're always going back to this. But and Smart, you can go using memory caching or kind of pass things through without having to go to this, and that's much more performant. So the way this is written is that still works, but it's also on the way, checkpointing things. So there's a couple of modes that you can run it in. You can run it in a mode where it is specifically writing to checkpointed, checkpointed outputs, and then the things that depend on that are reading from that within the same execution. But it can also be run in an asynchronous mode where you're checkpointing along the way, but you're still running it as if it were running it without having the dependencies go to those checkpoints. It can also be run in a mode where it just disregards the checkpoints, and that's probably what you want to do as soon as you get it right. This is more of a development assistant. But once you have things right, you probably don't need to checkpoint. You can just let it run without having it saved there. So persistent, this is between executions. So this is something where, and that's kind of a requirement, if you go and change your library, you can't, if you're running in a notebook, which you have all your code there, if you tweak things there, you can stay within the same execution and persist things and do that. But the moment you change things in a library you depend on, which is something that you might get into, you have to restart the execution in order to load in your new definitions. So when you do that, you lose all your persisted RDBs. But this is a way that you can essentially keep persisted RDBs, but between separate executions. And I suppose something that I neglected to mention is this also works between multiple users. So you can have multiple users if they are working on overlapping code bases and there's checkpoints there. It will just use the checkpoints that people used, that people have saved already. So that's the difference. These are essentially persisted RDBs that work between different Spark contexts. So yeah, one of the things that I kind of just glossed over is, so typically you're going to be saving these to HDFS. However, ideally, you would go to like an off-heap memory storage, like a Luxio, for example. That would probably be the fastest option here. So basically, there are these logical signatures that are generated, but you need some kind of base path to append that logic, that signature to. So you need to So there's a default path that is, temp directory of HDFS, but you could certainly change it so your base path is some other location, and it's just, you could have it in S3, you could have it in Eluxio, you could have it in HDFS, whatever kind of underlying storage that you want, you can set that as. And I'm sorry, could you repeat that? Yeah, so it's about the same as if you were, doing this in a manual way. So this is basically taking a manual technique that people will do, that is checkpointing intermediate results, and making it automatic. And it's So yeah, it depends on the particular pipeline and how it's broken down. So if you have something that, one part takes 10 minutes and the next part takes 10 minutes, if you checkpoint the first thing, then the second part will just take 10 minutes to run instead of 20 minutes from the beginning. Oh, interesting. Yeah, sure, we should talk. So unit tests are great. I'm not saying don't do unit tests and just run everything in production. Eventually, you are going to have to run it on the full set, and there's certainly a lot of bugs you can catch from compile time checks, unit tests, and small sample data sets that you can use to demonstrate that your thing seems to work on at least a small scale, and that people should definitely do that. The main reason why something like this is useful is because even when you go and do that, you run into things that you simply couldn't anticipate with unit tests. So there are situations where there are 1 in 10,000 elements in your data set might be having some kind of parse error on some logic you applied. And it wasn't in your sample set, wasn't in your unit test, and you didn't find out about it until you actually hit it. Of course, if you're working with nicely clean data sets, and you can avoid those kind of parsing problems if you have everything nicely structured with very normal things. That's great, but you don't always have that, and sometimes even when you have mostly that, it's not always 100%, especially when you're mixing different things. But I'm curious what you mean by the inline data quality things. We can follow up on that. Okay. I don't see any hands up. Okay. So, I mean, certainly, yes, all kinds of things. There are out-of-memory errors. There are logical errors. There are kind of, environment-specific errors that happen with your code. There's just all kinds of things that can go wrong. I wouldn't say that there's any that's like a particular pain point. But what I would say is the utility of this are for dealing with problems that you don't encounter at the small stage. So problems that you typically encounter at the larger stage when you have long execution times and you really need to prove it out and run it on the full data set. So the kind of problems that you run into there, that's what this is for. So this is just, it's still using Spark. It's just deferring its usage of the Spark context. So it works in a very similar, so Spark is lazy. You can kind of define a text file, map some things out of it, and those statements will execute instantly, basically, but then not actually compute the results until you do an action on it. And this works the same way, except one step further, in that it hasn't even defined the RDDs until you call getRDD, passing in a Spark context. So this parallelize is just a function defined. And certainly, if you have specific partitioning that you want to specify, you can still specify it in the same way. But it's just, there's no, everything's lazy. There's no actions to be taken on this until you say, until you plug in a Spark context. Well, we're not getting rid of the SC. We're just putting it in at a later step. We're starting without it. So one of the things that you don't have with that is you don't, and this is not that you have to stay without an SC, but it's just you can write a whole definition of a big thing without using a Spark context yet. And then at the end, you can plug in the SC and get an answer out of it. But I guess you won't be, you can define this pipeline where you're planning to get results and use those results as part of the pipeline. But yeah, that's basically it.